Okay, when we're looking at patterns of reproduction, we need to mention simulparity. This is where the members of a population have one reproductive event in their lifetime. And this would be your insects. When they reproduce a lot, but they don't reproduce but one time. Heteroparity is where the individuals in the population have many reproductive events in their lifetime, like most of the vertebrates, including humans, shrubs, trees. We have babies, 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 or offspring, offspring, and offspring. Now, exponential growth is the rate of population growth increasing as the number of females increases. More females, more births. Biotic potential is having a full effect and birth rate at a maximum during exponential growth. Full effect and birth rate is a maximum during exponential growth. And for exponential growth to continue, you gotta have plenty of habitat, food, shelter, and environmental factors can prevent exponential growth because food can run out, waste products can accumulate, competition can go up, parasites, diseases, all those things. So that can decrease our exponential growth or stop it even. What is environmental resistance? This is all the environmental conditions that prevent populations from achieving their biotic potential. Logistic growth. This is going to happen when environmental resistance slows exponential growth. When there's something that's going to prevent us from reaching our biotic potential and have full exponential growth, then we have logistic growth. And growing populations are eventually going to be affected by environmental resistance. Carrying capacity. This is how many individuals an environment can continuously support. And when you reach carrying capacity, the more likely the resources are going to become scarce. And so you're going to have more competition, more predation, all these things start to show up. Now, how can we regulate population size? Well, there are density independent factors. These are going to be abiotic factors, things that are non-living. The population density does not influence the intensity of the factor's effect. As I said, abiotic, natural disasters, storms, fires, floods, tornadoes, hurricanes, volcanic eruptions. Those are going to have the same effect if the population is big or small. Now, if it's a density dependent factor, it's a biotic factor, a living factor, where the population that's affected increases as the density increases. You have competition as an example, when the members attempt to use the same resources in a limited supply. It's going to have a bigger effect if you got a big population. Predation, where the predators eat the prey. If you've got a big population of predators. Parasitism, it'll weaken the host so they don't produce as many offspring. So those are density dependent factors. They are biotic factors. Density independent or abiotic factors. Here's an example of a density dependent factor, overgrazing. Look at the reindeer in 1910, 1920, 1930. We get to 1940 and we're up at 2,000. Suddenly there's a decline because of overgrazing. That's density dependent. The number of individuals in that population overgrazed, and so they started dying off. There was not enough food. Density independent would be a storm. If you have a low density of mice or a high density of mice, the storm still has the same effect. It's going to do the very same thing to the mouse population, regardless of how many members there are. The weather has no effect on no matter how big the population is. This is a density dependent effect. Competition. If you have a low density of birds, there's not as much competition for food. But if the high density of birds, you're going to run out of food faster. So they're going to start dying off. Another example would be the mice. If you have a low density, the predator is the hawk. But if you got a high density, you can have more hawks come in and there's plenty of food. So you got more predators going to eat more mice, so the mouse population is going to go down.